But for today, as promised, we are taking a break from Rage Friday, channeling our inner Ira Flato and contemplating our origin story with Niayesh Afshordi and Phil Halper, authors of Battle of the Big Bang, the new tales of our cosmic origins. This book is described as a thrilling exploration of competing cosmological origin stories, comparing new scientific ideas that upend our very notions of space, time, and reality. So I'm kind of hoping that maybe they'll tell us that we're all just dreaming right now or something, and that someday soon we're all going to wake up from this nightmare. Is that what you plan on telling us today, gentlemen?
Definitely.
Yeah, you got all right. Is there anything that I missed in your bios or anything that you'd like to add?
That's all good.
That was perfect.
Okay. I know everybody's eager to hear you, so I'm just going to turn it over to you, and I'll keep an eye on the chat.
So it's a pleasure to be here. Thank you very much for the invitation. I know I cannot see most of you, but I'm glad that everyone is here. Welcome. And I'm coming here. I'm actually warmer than where you are, I believe, or at least the weather is a bit nicer. In Ontario, Canada, so it's a bit chilly. And Phil is joining us from London, UK. And I guess you can tell us how the weather is over there.
Well, we do not celebrate when it rains here.
Right, yes. Okay, wonderful. So let's get us started. We are here to talk about the Big Bang. And there are many ways to start talking about the Big Bang. And we want to start with this story. Well, let's see, actually, can I move forward? Okay, so almost every culture has a creationist story. So Phil's favorite one is from the 3,000-year-old Hindu hymn.
One quick second. What we're seeing actually are your slides. So I'm wondering if you can make it so that we can see. There we go. I mean, wait. Oh, I see. We can see your script slides just so you're aware of that. I just wanted you to be aware of them. Okay.
Sorry about that. I don't know how that happened.
There you go. There you go.
Perfect. Yeah. Thank you.
Yeah. Okay. Right. Do you see the right one now?
Yes.
Okay, very good. Okay, so as I was saying, Phil's favorite, you can confirm that, he's sitting next to us. He emphasizes uncertainty, and this is from Nasadiya Sukta, which has a hymn of creation from Rig Veda, from 1500 to 1000 BC. So this is the original Hindu. You could see the translation. There was neither non-existence nor existence then, neither the realm of space nor the sky which is beyond. Who really knows? Who will here proclaim it? Whence was it produced? Whence is this creation? Gods came afterwards with the creation of this universe. Who then knows whence it has arisen? So what this hymn, which is 3,000 years old, emphasizes is the notion of uncertainty in creation. And even though we've learned a lot since then, and we've had many creation myths since, there is still a lot of uncertainty. And you may wonder if the Big Bang, which you learn in high school or primary school, depending on where you learn about the Big Bang, if at all, you may wonder whether this is just the newest creation myth. And this is an invasion of the Big Bang by Phil's friend, Nick Franco. And the answer to the question is yes and no. So in some sense, I'm not very satisfactory. So that's why we've written a whole book about this to answer that question. So how's the subject of today? So how this is the case? Is it, in what sense is Big Bang a creation myth, and in what sense it's not, is the subject of the book and today's talk. It all, like many things in physics, starts with Albert Einstein. And here is arguing with, in fact, a well-known priest, Georges Lemaitre, known as the father of the Big Bang. And in fact, they argued about whether there is a Big Bang or not. So Lemaitre came up with solutions to theory that Einstein had written. And that those theories or those solutions suggested that universe started at some point, universe must be expanding and must start from a Big Bang or something like that. So Einstein didn't like that. Einstein historically liked the static universe. So he said famously, "Vos calculus sunt corrects me vot physic est abominable." Now, I think last time I did this, I practiced my French. My French is not good, but I think that it's gotten worse since the last time. I should have practiced it, which means your calculations are correct, but your physics is abominable. Though you may also Google, if you use Google Translate, it says that your calculations are correct, but your physique is abominable. So not exactly sure which one Einstein meant by this. Nonetheless, Einstein's theory, Einstein, in spite of the predictions of his theory, he initially rejected the idea of an expanding universe. So in fact, his equations predicted it, or those were the only satisfactory solutions to his equations. But Einstein didn't like it. And in his theory, gravity is the curvature of space and time. And the mathematical formulation of that theory basically suggests that the universe cannot just sit there. In this theory, space-time is dynamical, is a living, breathing thing, and can expand and contract. And what Lemaitre has shown that it cannot just sit there. It must either expand or contract. So what changed Einstein's mind was the discovery that, in fact, universe was expanding. So first, Lemaitre said that it must be expanding or contracting. Einstein didn't like it. He actually tried to change his equation so that the universe wouldn't expand or contract. But nonetheless, in 1920s, this famous astronomer, American astronomer Edwin Hubble, used techniques that were pioneered by Henrietta Swan-Leavitt to measure distances to galaxies. So on the left here, you see this so-called Leavitt law, which relates the brightness of stars, variable stars, to the period of their variations. And by studying the brightness of the stars, variable stars in the sky, Hubble then basically used this law to show that when you look at galaxies, the farther away they are from us, the faster they're moving away from us. And that was, in fact, what was predicted from Lemaitre's calculation. It's now known as a Hubble-Lemaitre law that says that in a universe that obeys laws of Einstein's theory, if it's a homogeneous universe, things that are farther away, they are moving away faster from us through a law just like that. So that suggests that cosmos expands. And that brings us to our first battle. So we're going through some battles, and then I'm going to go through the first battle here, and then I'm going to switch, hand it over to Phil. But the question of whether the universe is expanding, and in fact, the fashion of its expansion, was the subject of the first battle. So we learned that the universe expands, but what does that mean? So there were two theories early on. There is the idea of the Big Bang, and there is a less known or now less known alternative known as a steady state. So if you have an expanding universe, this cartoon at the top shows this, there are two possibilities. Either as the universe gets bigger, if you look at the bottom, then things get farther and farther apart. So that's kind of what you expect. But there's a more kind of bizarre possibility that somehow as the universe expands, then you keep creating more matter out of vacuum, basically. So matter just constantly pops out of vacuum. You perform new electrons, new protons, new galaxies out of vacuum. So it seems kind of bizarre, and it violates conservation laws. But a lot of very well-known cosmologists liked it because it kind of didn't give you a moment of creation, if you want, a moment of a special moment in time. Because the Big Bang cosmology, where the galaxies are moving farther and farther away from each other, it looks like at some point everything is at the top of everything else. And that seemed like a special moment. And some physicists didn't like that. But on the other hand, I mean, it's not what we like about the universe that determines what the universe does. It's the observations and experiments. So that leads to our first battle of a steady state versus the Big Bang. So on the left, you have the well-known scientists who advocated for a steady state universe. You have Bondi, Gould, and Hoyle. They're all famous British scientists. And on the right is you had Lemaitre, who we already mentioned, Gamow, and Ryle. So Gamow and Lemaitre were both theorists. As you see, as I mentioned, Lemaitre was also a Catholic priest, known as also as the father of the Big Bang. And you had Martin Ryle, who was a radio astronomer. And really, the important thing is that it's the data or observations that distinguish between our scientific theories. It's not our beliefs. So this is our depiction of the battle between Hoyle and Ryle. So they had very heated debates. So Sermont and Ryle showed that the distribution of radio galaxies were getting denser in the past, backing the Big Bang model. So the Big Bang model, universe was denser in the past. The steady state, basically the density should stay the same over time. So the heated exchange between Ryle and Hoyle, there are famous narratives of that. So Woodruff T. Sullivan, who's a historian of radio astronomy, said Ryle and Hoyle would go after each other like a mongoose and a cobra. So that's the ChatGPT depiction of that debate, as you can see. But then there was a much more definitive piece of evidence, and that's the great thing about science, is that the data or observations get better and better, so we don't have to keep arguing about things because just the observations really just settle those debates. And that was the discovery of cosmic microwave background, which is the afterglow of the Big Bang. So if the universe was much denser and so much hotter at some point, then it would emit light, and we should see that light. That's something that's directly predicted from the Big Bang theory. But if the steady state is the right model, there is no period where the universe was much hotter. So that's like the sun. The sun is hotter, is hot, so it emits light. So the Big Bang was also hot, and it should have emitted light. The difference between the sun and the Big Bang is that the universe is expanding, so the radiation emitted by the Big Bang cools down over time because of cosmic expansion. And in 1964, the scientists depicted on the right, Penzias and Wilson at Bell Labs in New Jersey discovered a uniform cosmic microwave background noise at a temperature about 2.7 Kelvin, which is minus 270 degrees Celsius. I should have converted it to Fahrenheit. I think we should be, this is the first time I'm giving this talk in the US. So the Fahrenheit, it would be a very low temperature in Fahrenheit. But then this is not quite the right story. So this should have basically been the nail in the coffin for steady state. And they won the rightly Nobel Prize for this because basically it was a very definitive evidence for the Big Bang. But in fact, the cosmic microwave background was discovered by a Canadian 24 years earlier. And this is a picture of Andrew McCullough, who unfortunately died long before he saw the confirmation of this discovery. But he saw that, in fact, based on his measurements, astronomical measurements, he measured the temperature of interstellar space, and it looked like it was exactly the same temperature of 2.7 degrees above absolute zero. So that was, so go Canada. There we go. So I guess, hopefully this goes better when I give this talk in Canada and elsewhere. Okay, so moving on. So the cosmic microwave background that we observe, and we've observed it many more times over the years since its original discovery, seems to be almost perfectly uniform. But as you increase the contrast, you see a slight inhomogeneity, there's slight fluctuations in it. The tiny temperature variations of 1 part in 100,000. And that's a smoking gun of the Big Bang, not just the uniform temperature, but these tiny fluctuations, because now we could actually take a picture of the Big Bang if you want, see the contrast of what's going on. Now, in this picture, this red band that you see in the middle, that's just from our galaxy, but everything else, all the green and blue spots, those are fluctuations of the temperature. That was basically how the universe looked like. It was much younger than today, around 400,000 years old. Right, so I think I had that here. But then this brings us to the quintessential question of this talk. What came before the Big Bang? And we often hear that that question is meaningless. You might have heard it from many people, or you may even heard it from your teachers in high school or university. But it's not really a meaningless question. People may think Big Bang is the beginning of time, but that's not something that we know. That's just the beginning of the time that we can describe the universe based on the physics we know. So asking what came before the Big Bang must, well, it must be meaningless. But then, so the sense it is meaningless is, well, originally the reason people said it's meaningless is because of these theorems that were proved by the famous physicists, Roger Penrose and the late Stephen Hawking. Fun fact, Stephen Hawking, in fact, used to visit here often. So he used to sit next door here. And what they proved was there is a point where clocks stop ticking, basically. So that means that that's known as a singularity. So the point where you cannot kind of extend the time. So that was a mathematical theorem proved by these famous physicists. Penrose won the Nobel Prize. Hawking, unfortunately, didn't had passed away by that point. But what did they really prove? And were they really right to say that there is no time before the Big Bang? So they make four assumptions. One, the gravity is always attractive. Two, the universe has three space dimensions and one dimension of time. So that we can measure with rulers and clocks. Three, time travel into the past is impossible. And four, and most importantly, they use the mathematical equations of Einstein's theory of general relativity. So they showed that if use these four assumptions, then there's a point at which clocks stop ticking, right? So clocks can tick before any time after that point, but there is a point when you get to around 14 billion years ago also, where the clocks stop ticking. However, and here it is, surprise, surprise, most cosmology, including Penrose and Hawking, basically when he was alive, they concluded that these assumptions can be violated. Possibly all of them are violated, but at least one or more of them are violated. So there are really two Big Bangs, and it looks like they almost look the same here, although it turns out that there is a slight difference as it realizes. So you could play a game with this. So the small differences between these two pictures on the left and right, they're not that important. They are kind of two different versions of this from slightly different data. The one big difference is that whether there is a singularity, the point where the clocks have stopped ticking, or not. And these two Big Bang, we cannot really tell the difference right now unless we know the right laws that describe that point. Okay, so that singularity is what's really now suspect. So there is a hot Big Bang, whereas the story of what's going on here in this picture, you have an expanding universe, was hot early on, there were some quantum fluctuations happening early on, and then it cooled down over time. That's things that we kind of can more or less see and confirm. But then there is this idea of Big Bang singularity that's based on kind of pushing the laws that we know beyond the regime that we know they can be valid. And even though they predict something, we know what they predict don't make a lot of sense. So the Big Bang singularity is in some sense a mirage, but the hot Big Bang itself is established in physics that we know. And in fact, we did a survey recently with with Phil and my student Alice, many scientists at the conference, and we have in fact a more recent version of this survey. And there we asked them questions about fundamental problems in physics and astronomy. And there were lots of controversy. Nobody quite agreed on answers to any of these questions that we asked. However, there was one question that there was basically a majority agreement. Not everybody, obviously. There's always disagreements. But there is this question of, in your opinion, how should we understand the Big Bang? And 68% of physicists, of about 100 or so physicists who participate in the survey, say that it's a theory that says the universe evolved from a hot, dense state, that says nothing about whether there was an absolute beginning of time or not. So there was basically less than 20% who said that there was a singularity either with an absolute beginning of time, or absolute beginning of time with no singularity. So if someone says that it doesn't make sense to talk about or ask what was before the Big Bang, you should say, respond as 68% of physicists think that actually it does. And Big Bang doesn't say anything about whether there was a beginning or not. Okay, so what came before the Big Bang? It's not a meaningless question. And in fact, here I'm going to hand over to my co-author, who is a well-known YouTuber and science communicator. Here is from his interview with Stephen Hawking. Here is with Roger Penrose, the two basic pioneers of singularity theorems. And here are the two of us together. So now I hand it over to Phil, who's going to take us through the battle of inflation.
Okay, thanks very much, Niayesh. And I'm super jealous of everyone in Arizona because it's very cold here. Right, so the battle of inflation. What is this all about? Well, the first thing to say is that the Big Bang's been enormously successful, but is not without its problems. Now, we're not going to have time to go over all of them, so I'm just going to focus on one of them. So if you can go to the next, that's it. So we've got this thing called the horizon problem. So what is the horizon problem? Well, when a pizza comes out the oven, it cools to the temperature of the room, and I wish I had a hot pizza now. So now we enjoy its warmth because this takes time. It's not going to instantly cool down. It takes time to equalize with the temperature of the room. Next thing. Okay, and now the CMB. Here's the weird thing about it, or what I call the Canadian microwave background. It has almost the same temperature everywhere. Remember that slide that Niayesh showed earlier. Now, here's the very strange thing. In about 14 billion years, there hasn't been enough time for the CMB to come to equal temperature. So how did it become so uniform? That is the horizon problem. And a solution comes in the form of inflation. So inflation says the universe expands exponentially. So it would double in size. Some estimates have it as something like every 10 to the minus 37 seconds. So what's that? That's 10 trillionth of a trillionth of a trillionth of a second. And you just need less than 100 of these doublings, and all 4 of the Big Bang problems will be solved. So next slide. Okay, so let's go to the horizon problem, the one that we had in our sites earlier. So how does inflation solve the horizon problem? Well, in an inflationary universe, the cosmos would be vastly smaller 14 billion years ago than in the standard cosmology. So particles that have got time to come to equal temperature because they're traveling a much, much shorter distance. Next slide. So inflation is pretty mainstream here. The creators of inflation winning the prestigious Dirac Award. On the left, you see Alan Guth. He was the father of inflation. And then next to him is Paul Steinhardt in the middle and Andre Linde on the right. And they further developed the theory. So next slide. Okay, so what you see here is just to show you how mainstream inflationary cosmology is. You'll see a timeline of the universe. This is from the European Space Agency's Planck probe. And what they show is you get the Big Bang and then inflation. And most of the growth of the universe actually happens during the inflationary epoch. And then we get a sort of slow down and normal expansion. But I want to say this is wrong. And because inflation is actually a pre-Big Bang model. So let me justify this. Recall that cosmologists now define the Big Bang as the hot Big Bang. Remember that survey that we did? So inflation will actually cool the universe down to as cold as it can possibly be. Now, when inflation ends, its energy has to go somewhere. And it's converted into matter and radiation. And that is the Big Bang. So Alan Guth himself, you don't have to take my word for it, he said that inflation is a prequel to the conventional Big Bang picture. But that leads us to a rather strange result. Next slide. So this is called eternal inflation. So it's thought that inflation doesn't end everywhere at once. So like a radioactive decay, it happens with a half-life. But think about the part that hasn't decayed yet. What's that going to do? Well, it's going to keep on inflating. So it makes more Big Bangs. And this repeats endlessly. Inflation seems to make not one Big Bang, but an infinite number of them, a multiverse. Next slide. So there's an irony here, because that means that the steady state is in some sense back, because at the largest scales, eternal inflation is also static, just like the steady state was. So if you replace the galaxies at the steady state with pocket universes, you have kind of the same picture. And yet again, don't take my word for it. Alan Guth said that eternal inflation will strongly resemble the old steady state model of the universe. But the steady state was thought to have no beginning. Is that true in inflation? Well, inflation implies that gravity is actually repulsive. So that actually violates the singularity theorem of Penrose and Hawking. But, can inflation really be eternal into the past? Well, there has been a theorem proven by Borda, Guth, and Vilenkin that says no. Inflation is only future eternal. It is not eternal into the past. So it would still need some beginning. However, a recent work by Lesniewski, Exel, and Davis has suggested actually inflation can be eternal into the past, in which case there would be no beginning. And another study sort of said, well, maybe. And that study was done by Gesnajani, Ling, and Quintin, and the lead author on that is Niayesh's wife. So inflation is a prequel to the Big Bang, but it may not need its own prequel. But not everyone likes prequels, as we can see here from our poster of the Phantom Menace. And in fact, there's been something of a rebellion against inflation. Next slide. So what you see here is Paul Steinhardt is actually, you see there at the bottom right picture, you see Paul Steinhardt in the middle. He's been leading this rebellion with his colleagues Anna Eas and Avi Loeb, and they published a very harsh critique of inflation in the Scientific American, which sort of prompted dozens of cosmologists, including Stephen Hawking, to reply, defending the theory. But what are their complaints? Next slide. So there are various complaints. I won't have time to go over all of them. But one of them is that there are too many inflationary models. So there's various different ways that you can actually model inflationary cosmology. And there's so many, I couldn't even fit them all on the page. So that actually casts doubt on the claim. Just advance a little bit there, Niayesh. You obviously see these graphs and you say inflation matches the data. But of course, you've got to ask, well, which inflationary model matches the data? But I think the biggest objection to inflation is this issue of the multiverse. In fact, some have said it even threatens the integrity of physics, believing in these sort of unobservable realms. And Avi Loeb doesn't mince his words. I interviewed him and he compared the multiverse to taking recreational drugs. You will feel good. I'm sure Alan Guth feels really good about the idea of the multiverse, but doing physics is not about feeling good. However, Avi Loeb has been no stranger to controversy when he claimed that interstellar comets are actually alien spacecraft. So it's not clear who's on the drugs here. But, the critics say that inflationary cosmologists, they've abandoned the concept of empirical testability. I put that criticism to Alan Guth. Next slide. And he said to me, to assert that I claim that science needs to abandon the concept of empirical testability, in my view, is a blatant lie. So I did actually manage to host a debate between Alan Guth and another inflationary critic, so Roger Penrose. That's on my YouTube channel. Do check that out. It was a lot of fun. But we don't think scientific debates can be settled with YouTube chats. Instead, what inflationary cosmologists would like to find is the smoking gun of inflation. Is there such a thing? Well, you might have heard of something called B modes. So the idea here is that inflation produces ripples in the fabric of space-time known as gravitational waves. And these might imprint on the cosmic microwave background, Canadian microwave background, as these swirling patterns called B modes. So detecting them is thought to be our smoking gun. Although actually it's even more complicated than that. Well, but we go into that in the book. Now, in 2014, you might have seen the news that the B modes were in fact discovered. Next slide. So there's headlines from all these different news agencies talking about this spectacular discovery. There was talk of a Nobel Prize for Alan Guth and Andre Linde. Although I asked Paul Steinhardt whether he'd accept a Nobel Prize for inflation, and he said no. But the Nobel Committee didn't have to worry about that. Next slide. Because the discovery sort of turned to dust. So it turns out that in interstellar space, there is lots of dust. If you just click forward there. So that's a picture I took of the Wizard Nebula from my home in London. And you can see all these dust lanes. And it turns out that the B modes were probably just dust. So no discovery yet. And that has led people to look at alternatives to inflation. So what are these alternatives? So one idea is a cyclic. Oh, you're going to take over here, are you?
Yeah, and there's also a question. Irene, I think, asked a question. Did you want to?
Well, we can't. Let's see. Because we do a webinar format. So Irene, if you want to go ahead and put your question in the chat or put it in the Q&A, then we can go ahead and do it that way. So yeah, feel free to do that, Irene. And I don't know if Eddie can put Irene's virtual hand down, but you guys can go right ahead with your presentation.
Okay.
Thank you. Thank
you. Okay, thanks a lot, Phil. So now that Phil told you why inflation is so, on the one hand, so successful, but on the other hand, so controversial, it's natural to ask is this the only game in town? Are there alternatives? And it turns out that there are many. In fact, our book, we list 22 different alternatives. I mean, some do have a little bit of inflation in them, but yeah, basically there are many alternatives to inflation. But maybe the most popular is the cyclic universe. The universe goes through cycles that bounces, becomes very big, and then becomes small again. You have a big crunch and a big bang again. And these cycles can go in different ways. Roger Penrose has a different way that universe never really crunches. It just becomes infinitely large and suddenly forgets how big it is, if that makes any sense. It's known as conformal cyclic cosmology. So a cyclic universe can mimic inflation. At least in some versions, there might be inflation. In other versions, a universe expands and contracts. So this one that I showed you is Roger Penrose's, which does never contract. And somehow just at one point, universe forgets how big it is. And the universe at the Big Bang and far future can't build rulers or clocks. So that's why it can be a very big universe and a very small universe. They can be confused with each other because there are no rulers and clocks left. So that was Roger's model, but there are other cyclic universe models. Basically, in all of these models, you kind of transform from one ion to each other, either through collapsing or through this forgetting of the scale, otherwise known as conformal rescaling. But there are others. One that I worked on is what if universe starts or comes out of a black hole? This is known as a black hole genesis. So this is a movie that Phil made for one of his YouTube videos on our black hole genesis models. And the idea is that our universe comes out of a 5-dimensional black hole, and we live somewhere on the surface of this 5-dimensional black hole. And that actually was on the cover of Scientific American about 10 years ago. So you could, did black hole come? The black hole at the beginning of time. That was the title. Other alternatives, maybe the universe wasn't very small or didn't come out of a black hole, but somehow light behaved in a very different way at early times. Universe could become homogeneous, or different parts of the universe could be in contact with each other, not because it was very small, like in inflation, but rather because light could travel much, much faster. And that actually can solve a bunch of problems. So that's kind of an animation of this, that the universe starts with light much, much faster. And then over time, basically, light that slows down becomes like it is now. Or everything can travel much, much faster. So all of these theories have their own predictions, but you may ask, okay, so even if there is inflation, or even if you don't have any of these alternatives, you could still ask, if inflation happened, what came before? There are different ideas. As we said, inflation should have a beginning according to some theorems, at least, if you believe Borde, Guth, and Vilenkin. So maybe it tunneled out of nothing. So Vilenkin, who is a well-known cosmologist, Alex Vilenkin, he suggested maybe universe tunneled out of nothing, just a space and time didn't exist, and at some point there's a quantum fluctuation that generated universe. So particle physics, that can happen. We know particles can fluctuate in and out of vacuum. That's how you have Hawking radiation. But what if a space itself is can behave the same way? There is no space, and then suddenly a space fluctuated into existence. And that's another possibility. So. And that leads us to the next battle, which is basically what the real battle that we have to address when we're talking about the beginning of the universe, which is, do we really have the laws right? Any of these theories require, any of the scenarios I described to you, either inflation or without inflation, you are kind of venturing to a regime where the laws of physics probably look very, very different from the laws that we see, and we have good reasons for that. And that has to do with basically battle of quantum gravity, which is the holy grail of theoretical physics. So the real question here is, can the rules of quantum and gravity work together? Now, the rules of quantum, of course, on the left, your cell phone, the lasers, everything you work in, how you can hear me, these work based on these devices use rules of quantum mechanics. On the right, you have gravity, or satellites, communications, GPS, the famous black hole pictures, gravitational waves. Those obey rules of general relativity that are also very successful and well tested. But it turns out that both these theories, even though they are very, very well tested and successful on their own arena, they don't work together very well, unfortunately. And that have led us to the quantum gravity zoo, basically all the attempts to unify these two sets of rules. And I'm not going to describe any of these, but these are like 6 of these possible proposals to how you unite quantum mechanics with gravity. And they all are very bizarre and different. Like a string theory assumes instead of particles, you have fundamentalist strings, but you also have 6 extra dimensions that we don't see. Maybe the space is discrete. Maybe basically, maybe you don't have relativity and fundamentalist case, they are preferred time or ethers. Maybe universe is a fractal, and different ideas out there. And they all tell us something different about the early universe. The most popular one is known as a string theory. So replace point particles. It gives finite numbers for the predictions of physical processes, and gravity kind of emerges from particle physics. But as I said, it needs 6 extra dimensions and some thing known as supersymmetry, none of which we actually see. So even though this is the most popular approach to quantum gravity. A contender is known as loop quantum gravity, which makes the space and time discrete. So that's actually where I am joining you right now from. Parameter Institute is one of the hubs for loop quantum gravity. The founder of it is here, one of the founders, Leah Smolin. So in this theory that the space is discrete, there's some fundamental discreteness, and the space cannot be basically infinitely compressed. So that avoids the singularity. So you don't need extra dimensions here or supersymmetry, but cannot explain other forces of nature. So again, Phil hosted another debate between Carlo Rovelli and David Gross. Carlo Rovelli was another founder of loop quantum gravity. David Gross is one of the pioneers of a string theory, and they battled it out. And then you could also watch that and decide for yourself which one of these gentlemen is more convincing. So there are many ideas for string cosmology. Maybe these extra dimensions could help us in resolving the Big Bang or resolving the singularity. Maybe the gas of strings was really the right picture of the hot Big Bang, not the gas of particles. Maybe you have actually one less dimension at early times. So somehow the dimension of time emerges. This is known as holographic cosmology. So these are all kind of different directions that the string theory could help us, but I think the problem is there is no unique one. We're not sure which one of them is actually right. And in fact, here one of the founders, a father of a string theory, Gabriel Veneziano, suggests that maybe a string theory says that string theory itself gives you a pre-Big Bang model. So Big Bang was not the origin of the universe, but simply outcome of pre-existing collapsing universe or contracting universe. So, this is an example that quantum gravity, at least in view of Veneziano, the father of string theory, says that Big Bang was not the beginning of time. Look, quantum cosmology predictions. So again, these are the small in, but there are others. Sorry, go ahead.
No,
okay.
I couldn't. You broke up for a second there.
Okay. But can you hear me now?
Oh, good.
Okay, very good. So, and they suggested that basically instead of a singularity, you have a bounce. Universe contracts, reaches some maximum density, and then expands again. But then not everybody agrees with that picture. So, what's going on? Okay. So what do these approaches have in common? Big Bang was not the beginning. 14 billion years ago, something was very dense and very hot happened. But that's only a lower limit on our cosmic age. Our universe could be much, much older than 14 billion years. And that brings us to, in some sense, that sounds like the question of religion. Was there a creation or not? And that brings us to our maybe one of the most heated debates or battles we have, the battle of science and religion. And here I'm going to hand it over back to Phil.
Thanks, Niayesh. All right, so let's go to the next slide. So big question is, can the Big Bang actually prove God? This is what some people have suggested. And of course, the father of the Big Bang is Georges Lemaitre, and he was a Catholic priest, so you might expect him to say yes. But actually, he said no. He wanted to keep his faith and his science completely separate. And he was very, very upset that the Pope tried to use a Big Bang to prove Genesis. But there's a religious philosopher you might have heard of called William Lane Craig, and he says the answer is yes. And he's got this argument, which goes like this. It's called the Kalam cosmological argument. It says that everything that begins to exist has a cause. The universe began to exist, therefore the universe has a cause. But we don't know. Craig uses the Big Bang to defend premise 2, but as we've said, we don't really know if the Big Bang was the beginning, and nor do we know, if causality is fundamental. So I don't think that we should buy into this argument. The universe might have had a beginning, might not have. Even if it did, it might not have a cause. But I do wonder, although this argument I think doesn't work, it might be possible to make a universe in a lab. And Fari Guthenguven has suggested a mechanism. And what's weird is that the bubble universe that they create would actually pinch off. So you wouldn't be able to communicate with your creation. There'd be no reason to think the creator would be a perfect being. And although Alan Guth, he's a very nice guy and obviously super smart, he did win an award for having the messiest office in Boston. But if you were to create a universe, would you sign your initials in your creation? So this is our picture of the oldest light of the universe. Anyone see any initials here? I think I see the letters S and H. Does anyone? Yeah, maybe you can see that now. So my suspicion is that Stephen Hawking created the universe, and he created maybe he could have used a time machine to go back in time and create the universe. If you go to the next slide, Niayesh, there have been suggestions that actually there are solutions to Einstein's equations that allow for backward time travel. And there are two sort of different versions of this. The one on the right has the time loop right at the beginning of sort of eternal inflation, and the one on the left has the whole universe as one giant time loop. That's actually a model that Niayesh worked on with his student Beth Gould, and they call that periodic time cosmology. But I like to call it the Groundhog Day universe. So there's, if you go to the next slide. Okay, so this is all quite speculative stuff, right? The final battle has to be to actually put this stuff to experimental tests. We shouldn't believe any of these models until they have been tested. So the bad news is that unfortunately with the Trump administration, most of the projects for astrophysics have been cancelled. In particular, there was one called CMBS4. That was going to be the next project, big project for looking at the cosmological background. That's been cancelled. But, you know, on the optimistic side, politics comes and goes. So the thing that I'm excited about is a new possible way to probe the early universe, to go back way before the cosmic microwave background. And this is from gravitational waves. These are ripples in the fabric of space-time. They were detected from colliding black holes, and they can travel through the fog of the early universe. So we cannot see light older than the CMB, but gravitational waves we can do. So some models predict they exist, like inflationary cosmology, and others say they don't. And different models of inflation or different cyclic models might predict different patterns in the gravitational wave background. So this, I think, is our best chance to sort of put these models to the test. And how we do that? Well, one, we can go to the next slide, please. We can go to the ground and keep looking for those B modes, because although we didn't find them in 2014, and that was disappointing to some, I mean, other people were happy. We might find them tomorrow. We don't know. So we keep looking. This is the Simons Observatory. They're looking for B modes. And then if they are found from the ground, we want to sort of have a more accurate characterization. So that would be a space-based mission. Next slide. And this is called Lightbird. The Japanese are leading this. So most people think that that is the next CMB mission to probe for these B modes. But beyond that, there's something much more ambitious, which is to take these giant gravitational wave detectors and put them into space. And there's a project called LISA, but then beyond LISA is another one called Big Bang Observer. And that would be our best shot for getting data on the very birth of our expanding universe. And maybe we can find out whether there was something before or not. So the final battle is not with our colleagues or fellow citizens. Our true struggle is to overcome our ignorance, our adventure to comprehend the cosmos, ourselves included. Our process is a scientific method, honed in solving cosmic mysteries, but all derived from all other aspects of our humanity. This will be our ultimate survival tool in an ever-changing world. The power to remember our past lies in your future. Thank you.
Thank you. You're muted, Jean.
Sorry about that. Okay, thank you for that. I wrote that down. Our struggle is to overcome our ignorance, because in my work, I feel like that is what because what we do, what part of my job is really looking at every level of government and Christian nationalism. And here in the United States, obviously, we have a real problem with white Christian nationalism and Christo-fascism taking over. And the biggest problem with these people who just they desperately cling to these ideologies that they have, and if they would just try to overcome their own ignorance, it could be magical. There is one question up here in the chat that comes from Phil. And I commented in the chat. I said, I don't know if I feel smarter now listening to you two or less smart, but either way, I've learned something. And Phil clearly is much smarter than I am, because he says, in the expanding and contracting cyclic universe model, given that the expansion of the universe is currently accelerating, what would cause the contraction in the future?
Good.
Niayesh, do you want to take that, or shall I do it?
Phil, you take it. Go ahead.
All right,
Phil.
okay. So basically, what you have to try and figure out is what is the nature of this dark energy that's causing the universe to accelerate in its expansion. So one hypothesis is it's what's called a cosmological constant, which basically means sort of energy of the vacuum. And if dark energy is a cosmological constant, then the universe will not recontract. However, there are other interpretations of the dark energy. So some is that it's a time-varying field, or others is that it's some effect of quantum gravity, or, you know, there's various other fields. Bottom line is there's various different proposals for what is causing dark energy. Now, something very exciting that's happened recently is, and I was very lucky to be asked to help announce these results. So I actually got to know them a couple of weeks before they were announced. But there's this thing called the Dark Energy Spectroscopic Instrument, and they've taken some of the most accurate measurements of how dark energy is behaving over time. And what they find is that it is actually changing over time. So that would mean it is not a cosmological constant. Now, I don't want to get too excited about that yet, because any new exciting finding in physics has to be confirmed by follow-up. And more often than not, the exciting find turns to dust, like we saw with the B modes. So certainly don't get too excited, but you can, I think, allow yourself a little bit of excitement that it may turn out that the dark energy is not a cosmological constant. And if it's something varying over time, then it could reduce and maybe even go negative, and then it could cause the universe to recollapse.
Okay, let's see, there's another, I think there's a question. It's very long, so let's pay attention. This one comes from Erica. She says, I've long thought that the populist vision of the BBT, a bang followed by infinite expansion, end of story, suffered from the same basic problem as the Ptolemaic model of the universe. It assumes that we are special, our existence is special, so therefore the existence of the universe is singular and special. Seeing the universe as a singular event that starts at a bang and expands into infinite entropy kind of suggests that we exist in a unique event, much like saying the Earth is the center of the universe. I think any theory that appeals to the human ego should be viewed as suspicious. It shouldn't mean it's wrong, but it should be subject to a heightened level of scrutiny. I find a theory that says that our universe is not special, but in some way is just one part of a much, much larger and infinite pattern, much more appealing. A question that comes out of that is, in the scientific community, here's the question part, do theories that have an undertone of human specialness get any level of challenge on that basis?
I can take that, but that is an excellent question and very thoughtful question. Well done, Erica. And indeed, this goes back to for a century. I mean, I think this starts from the steady state that I mentioned early on. That indeed, exactly what makes you uncomfortable is what made Bondi, Hoyle, and Gold uncomfortable. That why should there be a special moment? Maybe every time the same point, we are not at the center of the solar system. Why should there be a special time where was the Big Bang and we happen to be just after that? And but then you see, we all have our philosophies, and then ultimately the nice thing about science as opposed to philosophy or religion is that we let the data guide us, and whatever our preconceived notions are, the observations are what really guides us. And sometimes our intuitions are correct, and other times, more often than not, our intuitions are incorrect. And indeed, the same discussions are going on now. So there's different version of a steady state, as Phil mentioned, is this eternal universe, the multiverse, which, yeah, maybe that kind of conforms more with the picture that you're advocating. But as I said, the same as the previous time, it's really about the data and observations. We may have our own preconceived notions of how things should work. But if you cannot test your ideas or your philosophies with observations, that's outside the realm of science. And then basically we're not talking about scientific ideas. So it's an excellent question. And then these debates are still going on. But ultimately, you have to be able to test your ideas with data. Otherwise, I mean, scientists don't like to talk about it, basically. Well, I guess some of them do talk about it, but then it's not really science. Oh, you're muted, Jean, again.
I do have another question. And I also, unfortunately, I have another event like that. Well, my grandson's here. My grandson's here, and I have to watch him in about 2 minutes. So Alex does have a question. I'm not sure if you can answer it in 2 minutes, but he says, given the rate of discovery in astrophysics, how well does the science presented in the debate between Sean Carroll and Dr. Craig hold to the modern models in cosmology?
Okay, I can take that one. I know Sean quite well. I think, well, what I would do is check with Don Page, because Sean did the debate with William Lane Craig, and he got a letter from Don Page. Now, who's Don Page, you might ask? He is a former student of Stephen Hawking, and he's become a famous cosmologist in his own right. There's a thing called the Page Time named after him. And he's an evangelical Christian. And he wrote a letter to Bill Craig saying, I think Sean got all the science right in the debate. So I think, yeah, I think Sean basically picked it right. We're kind of on the same page as him, I think. So basically, the two big topics that they were debating was, did the universe have a beginning? And then there was also this fine tuning of the universe issue came up. So Sean basically said, we don't know if the universe had a beginning. And Bill Craig said, we do. It definitely did. And what we argue in the book is basically Sean has got it right. And Don Page, an evangelical Christian, also said that Sean got it right. We don't know if the universe had a beginning or not. It might have. Like, I definitely don't want to say that it didn't, but at the moment, we can't say, because there's that distinction between the hot Big Bang and the Big Bang singularity, and all the evidence is for the hot Big Bang. The Big Bang singularity, not so much. So on the fine tuning, I mean, Sean made a number of points that I basically agree with. First, basically, we did a survey of physicists, actually. I think this might be of relevance. And they were kind of all agreed that, well, I wouldn't say all agreed, mostly agreed that an intelligent designer is not a good explanation for fine tuning. So basically, Sean was like, well, we're not sure if there is fine tuning. It's not clear. Maybe there is, maybe there isn't. And indeed, in the survey that we did, the most popular view was that fine tuning is kind of a pseudo problem, that there's really nothing to be explained. You can't really say anything about the probability of our universe having certain values, because if you only have one universe, what does probability even mean? So I think that was the most popular view. Now, the multiverse was the second most popular view, and Sean sort of said, okay, if there is fine tuning, we've already got a good explanation. It's the multiverse. One thing I think that Sean didn't say, what he didn't really go over, was actually there's a fair bit of support for two other options. One is that maybe the fine tuning is explained by some underlying principle, that maybe the constant nature have to take on the values that they do. Maybe there's some dynamical theory that will tell you these values have to have certain things. There is a theory called asymptotically safe gravity, which I think predicted the Higgs mass, and is kind of maybe in that line of thought. And the other explanation for the fine tuning is maybe the cosmos could undergo some kind of natural selection. And Lee Smolin's proposed a model like that, and he's at Perimeter with Niayesh. So I think there are actually more options than what Sean suggested. But the important thing to know, if you want to know what the opinion of physicists are, they're kind of all over the show on this. And the idea that fine tuning is the sort of pseudo problem is the most popular single answer, I would say.
Well, I say you've given all of us something to contemplate for the weekend, and it's far better than, I mean, usually we get all worked up into a rage on Friday, so we're really happy that you've given us something to think about, and not something necessarily to stew over in a bad way. So thank you so much.
Thank you for having us.
Thank you. This has been amazing. I appreciate you both. I hope everybody has a wonderful weekend, and take care. Bye, everybody. See you later.
Bye.
Thank you.
Great. Thanks, everyone.